Welcome to the second half of Chapter 3 of Surviving Statistics. In this second half, we're going to talk about the measures of dispersion, and we'll also talk about the empirical rule. In the first half of Chapter 3, we talked about measures of central tendency, where we were trying to describe the center point or the average value of a variable within the data set. Well, now we're going to move into a little bit more difficult area, which is measures of dispersion. Measures of dispersion still are descriptive statistics, but these measures tell us how widely our data points vary or how widely they are dispersed. And most often we're comparing the dispersion to the mean. So why are these so important? Well, let me give you an illustration to help you understand why measures of dispersion are important. Well, here's kind of a silly example of why measures of dispersion are so important here. So just as an example, I live in an area of Idaho where the two rivers, Clearwater and the Snake River, meet. Now, one of the most popular activities is in the summer is to drive up the Snake River on the Washington side and throw out a raft or a canoe or an inner tube and float down. Now, I've done that only once, and it wasn't a really great experience here, but we'll get into that another time. So let's assume someone invited you to float down that river, and but you can't swim. And so you talk to a local, and the local says, hey, don't worry, the mean depth of the river is only 4 feet. You could get up and walk any time. Well, that's a descriptive statistic, the mean. And it might be correct, remember, but that's just the average value. There are going to be lower values than that and higher values as well. So this local is probably trying to drown you, or they just don't understand statistics. So measures of dispersion are very, very important to us. So now that we've explained why measures of dispersion are so important, let's talk about one of the easiest to compute, and that's the range. The range is simply the difference between the highest value and the lowest value. So looking at our test scores that we've been working at this chapter, notice that the highest test score was 100. That was the student who cheated, and the lowest test score was 7. So in this case, the range would be 34. That's quite a large range for these test scores here. And just an FYI, the Snake River is actually up to 250 feet deep near Lewiston, and so no, you can't get up and walk at any time, even if the mean depth is only 4 feet. As we continue on through this textbook and statistics, we will be referring to using Excel more and more. Now, Excel does not have a range function, but it does have two functions that allow you to compute the range. It has the max function and the min function. And so here on the screen you see an example of how to use that, even for a very large list of data, to compute the range using both the min and the max functions. Well, now that we dispense with the range, we'll get into one that's slightly more difficult, and that is the variance. And the variance is a measure of variability, primarily telling us how far each value varies from the mean. Now, as we did with the mean, there were two formulas, but they really weren't different in their computation for a sample and a population. We will actually have two different formulas that we use, depending on whether the data is coming from a sample or a population. All right, let's get started with the population variance. And so here on the screen, you see the formula written out. Let's just kind of go over it. It looks rather daunting at first, but it really isn't. It's actually pretty simple. So we represent the population variance with sigma squared. Now, we compute that by taking the sum of x minus mu, okay, x being each individual value, subtracting mu, the mean, then notice that's mu, which represents the population mean, and then we square that. So we take the sum of the difference between each value and the mean, square it, and we divide it by n. In this case, we're using a capital N, which represents the number in the population. All right, let's see how this works. We're going to take this step by step using our test scores example. So our first step is to compute the population mean. Now, of course, we just do that by adding up all of the values and dividing it by the number in that population. Again, we're assuming this is a population this time. So we have a mean of 72. Then the next step is to compute the difference between each value and the mean. So you see in the table here, I've done that. So we have x is 100 for the first value. We have the mean of 72, which is consistent. And then we subtract the difference. And so the difference for the first one is 28, and so on. We have -4 and down. Again, we're taking this step by step Some of you can probably do this in your head, but sometimes I'm not too good at math, so I just like to take it each step by step. And so the next step, after we have found out what the difference is between each value, x and the mu, we then square the difference. And you'll notice that we have a very large squared difference for the first value of 100 because it does deviate from the mean substantially. All right, once we've done that for all of the values, the next step is to sum the squared differences. So at the very, very bottom here of this table, you see that the total, or the sum of the squared differences, is 918. And finally, using the formula that you see here up on the screen, we divide the sum of the squared differences by the number of observations in the population. So 918 divided by 7 gives us 131.1429. So our population variance in this case is 131.1429. Quite a large value, but that's because we do have the outlier in here. And so the outlier is still affecting the variance. As I mentioned, we have a very large variance, and the variance is larger than any of the values that we have, but that is what we're trying to see. So by computing this, because of that outlier, we see that we have a very large dispersion or variance in these values. Within statistics, you'll be dealing with samples more than populations, and so you'll probably be using the sample variance more than the population variance. But let's look at the differences in the formulas here. They look a little different, but they're really not a whole lot different. We're just using different symbols to represent similar things. So at the top right, we see the population variance. Notice that we're using sigma squared. It's the sum of x minus mu squared up divided by the number of observations in the population. Now on the left side here we see the sample variance. The sample variance is represented with s squared, and the formula for it is x minus x bar. So rather than the population mean, we're subtracting each value from the sample mean. We're squaring that. And then in the denominator, notice that we have lowercase n, which represents the number of observations in the sample minus 1. So we are subtracting 1, and so that'll give us a different value than if we were computing the population variance. All right, let's step through computing a sample variance, and once again we'll use those test scores. This time we're going to assume it's a sample of the class, not the entire class. So the first thing we do is compute the sample mean. Well, again, we compute that the same way we compute the population mean. We add them all up, we divide by the number of observations, we end up with 72. That's the first step in computing the sample variance. And just as I did when we computed the population variance, we're taking this step by step. And so the next step, step 2, is to compute the difference between each value and the sample mean. And so this table displays that. We have each value x, and we have the x bar, and of course the difference between the two. The third step in computing the sample variance is to square the differences between each value and the sample mean. So you can see on the screen that I've added another column here that takes x minus the x bar and squared that. Okay, the last two steps in computing the sample variance longhand, or the long way, is to sum the squared differences. And so we've done that, and we end up with 918. Then the next step is to divide the summed squared differences by n minus 1. Remember, this is a sample now, and there were 7 observations, so the denominator is going to be 6. So 918 divided by 6 equals 153. Now notice, if you recall from a couple of slides ago, the sample variance is a little larger than the population variance, and what we're trying to do is eliminate bias. We'll talk about that here in a bit, by subtracting 1 from the size of the sample. As I just mentioned, we end up with a larger sample variance than the population variance using the same values. And again, the reason for that is that we subtracted 1 from the sample size, making the denominator smaller. Now we did that, as I mentioned before, to reduce potential error or bias from the values that we compute from samples. In case you haven't figured it out by now, I love Excel. Excel does all the math for me. Now I do think it's important for us to understand how to compute a variance longhand, and we went through those steps. But if you are an Excel fan, or another spreadsheet fan for that matter, those spreadsheets have functions that will compute variances for you. In this example, you see the insert function dialog box, and we see a couple of VAR formulas or functions that we can use to compute the variance. The P stands for population, and the S for sample. So if I was going to compute a sample variance, as we just talked about, I would just use the VAR function, and I'll show you how that works in the next slide here. On the screen, you see that I've used both the population variance function and also the sample variance function with the values for our test scores. And of course, there's a difference. We end up with a little larger value when we're computing a sample variance. And we explained why, because we subtract 1 from the denominator to eliminate potential errors that we see from samples versus populations parameters. We spent a lot of time talking about how to compute the sample variance and the population variance, and now I'm going to tell you that we really don't use the variance that much as a standalone value in statistics. What we use most often is standard deviation. However, the standard deviation is derived from the variance. So take a look at the formulas that you see on screen here. Population standard deviation is simply sigma, which equates to the square root of sigma squared. Makes sense, right? The sample standard deviation is referred to as S, which is the square root of S squared. So it's simply the square root of the variance. And so once you've computed the variance, you can very easily compute the standard deviation. So looking at our sample variance that we computed just a few minutes ago, using that formula that you see on screen here, we ended up with a sample variance of 153. Well, we take the square root of that and we end up with a sample standard deviation of 12.3693, and it's a lot smaller and easier to work with than the variance. And we'll see how that works when we start getting into the empirical rule in just a couple of seconds here. Now, before we talk about the empirical rule, let me remind you again, because I love Excel, Excel does have a standard deviation function, and you can even bypass the variance altogether and just compute the standard deviation of a range of either sample or population variable values. You'll see, just as we had with the variable .p versus .s in this version of Excel that you are seeing on screen here, the .p represents the population standard deviation, and the .s represents the sample standard deviation. All right, it's time to talk about the empirical rule. And the empirical rule relies upon the normal bell-shaped curve that we use so often in statistics. So if our data is distributed in a normal curve, and most of the time it will be, and we'll talk about that as we get further down the road here, the empirical rule lets us guesstimate how many observations are going to fall within certain values. So if you can look at the example normal curve that you see here, we have a mean of 100 and we have a standard deviation of 10. Makes that very, very easy to work with here. So the empirical rule tells us that 68% of the values are going to lie plus or minus 1 standard deviation of the mean. So in this case, with a mean of 100 and a standard deviation of 10, if we collected 100 people in a sample, we could be sure that 68% of that sample would have their value between 90 and 110, again assuming that the data is normally distributed. It also tells us that 95% of the values are going to fall plus or minus 2 standard deviations of the mean, and we'll develop that a little bit further in the next slide here. So again, if our data is normally distributed, the empirical rule tells us how many observations we can expect to fall within certain values. So as I mentioned, 68% typically will fall between plus or minus 1 standard deviation of the mean. 95% will fall between plus or minus 2 standard deviations of the mean, and practically all, 99.7, will fall plus or minus 3 standard deviations. So again, the way this works, we're starting to get ready to do some inferential statistics. If I were to do a sample of 100 people and the mean turned out to be 100 and the standard deviation turned out to be 10, I could be relatively assured that 68% would fall between 90 and 110, and 95% of the people, or in whatever I happen to survey, would fall between 80 and 120. Well, we made it through Chapter 3, both Lesson A, 3A, and 3B, and so let's review what we've done in 3B. We talked about measures of dispersion. We need to know how far our values disperse from the mean. We talked about the range, which is the largest value minus the smallest value. We talked about the population variance and the sample variance, and notice that with the sample variance we subtract 1 from the number of observations in the sample. We talked about using the standard deviation more often than the variance, and we see that we can easily compute the standard deviation by just taking the square root of the variance. We talked about the empirical rule, and if our data is normally distributed, 68% of the values will lie plus or minus 1 standard deviation from the mean, all the way to 99.7 will lie plus or minus 3 standard deviations from the mean. And remember, Excel has built-in functions for almost all of these, especially the variance and the standard deviation, to help you out. And remember, all of these lessons are based on my textbook, Surviving Statistics, which is available on Amazon. And do remember to check out my website for downloadable files, calculators, and other resources.